I will begin with a word of prayer. So, I'm going to start talking. Dear Father, we thank you for this day again. I thank you for these students in this class. Just ask you to bless our work today, Lord. In your name I pray, Lord Jesus. Amen. All right, so let's take another look at orthogonal trajectories. This is a very standard problem. And most of you didn't know what to do last time, but I'm assuming that's probably just because, the word orthogonal trajectory escaped my mouth at some point in the first week. It probably went past you, just glazed on by, and didn't stick. So let's try it again. So basically the idea is, if your given curve has dy dx equals to, let's say, Pac-Man, then you solve dy dx equals to -1 over Pac-Man. All right? That is one way you can find the orthogonal trajectories to a given set of curves. Right? Another way this comes to you is your given curve has f of x comma y equals to 0. Right? You've got some equation that defines the curve, right? So then what you do, yes, indeed, partial f partial x, whoa, dx plus partial f partial y dy equals to 0. And so, all right, at this point you can go, okay, so dy dx is what? It's apparently minus partial f partial y divided by partial f partial x, right? If you solve this equation for dy over dx, that's what you get. And indeed, that's the relation. That's how the slope of a curve which has level equation big F equal to 0 is governed by the partial derivatives. It's related to the quotient of the partial derivatives in that way. And so if you solve this equation, you would not get orthogonal trajectories, right? You would get the trajectories. Well, you wouldn't get just one curve, right? If this is a single curve, right? If this is a single curve, the solution to this is going to give you a whole family of curves of which that is one member, right? But if you want to find the orthogonal trajectories to this given curve, you again, so to find orthogonal trajectories, you solve dy dx equals to, partial f partial x, my bad, partial f partial x divided by partial f partial y, right? So again, if this thing is Pac-Man, this what I wrote over here is -1 over Pac-Man, right? There's another way you could look at this. If you're given p dx plus q dy equals to 0, you can instead solve q dx minus p dy equals to 0. So this gives orthogonal trajectories to solutions to that guy. So that pretty much covers all of the ways this can come at you, right? So that's one comment I wanted to make, because there's, grading your quiz. And when I say grade, I mean that very loosely. You either have an 8 or a 9. I would have given you a 10 if it was perfect, but that was nobody. Some of you were half true. I gave you guys 9s. Nobody really got both problems, I don't think. If you did and I just missed it, come to me after class. I'll give you back your point. I don't mind. But I didn't want to be too strict on the grading of this last quiz, because, I just don't want to. So, all right. So let's see here. I think what else I was going to tell you about these things. Here, let's look at a particular one. And this middle option, sometimes it's annoying. It could be something like this. You could have something like, and I might get stuck on this, guys. Y squared minus, oh, I probably shouldn't even do this. Yeah, let me not make examples that are like stupidly hard in class. Let's see here. X squared, suppose we're looking at x squared minus y squared equals to 3, right? That is a particular hyperbola, right? The asymptotes are y equals plus or minus x. It opens horizontally, right? So like this thing, it's got y equals plus or minus x for its like asymptotes. It's got vertices. If you plug in y equal to 0, you get x is plus or minus root 3. So there you go, that's the graph. Something like that, okay? And then we'd like to find the, so my problem then is, the question I'm asking is, what are the orthogonal trajectories to this curve? All right? So I have to figure out, first of all, what's dy dx, right? So this tells me that 2x dx plus 2y dy is equal to 0. If you believe my third bullet point, sorry. There, I'm an idiot. I should put silencer on my gun. Let's see here. But then I have to pay like some exorbitant tax, right? Doesn't make any sense. Why is there crazy tax on silencers? If it wasn't for that stupid tax, you wouldn't have to hear the rednecks shooting their guns so much, right? Let's see here. Oh, you guys don't live out in the woods. Never mind.
Doesn't work for trucks.
What's that?
Doesn't work for trucks.
Doesn't work for trucks. It's true. So if I trade that for that, I find the orthogonal trajectories. See what I did? I flipped these and I put a minus on one of them. That amounts to looking for the solutions which have the negative reciprocal of the slope. And then, well, this is not exact, right? So I can't just, it'd be nice if you could say, oh, that's the differential of such and so forth done equal to a constant, right? We can't do that here. So I'm just going to go back to our usual method, solve for dy dt. Oh, man. Whoa. Dude. No. That's not good. How about a y? Would that be better? Yeah. All right, so that gives us dy dx equal to what? Add the other thing, so I get a 2y over 2x, right? Let me just check it. If over here I'd solve for dy dx, what would I have gotten? Dy dx equal to what? Minus 2x over 2y, right? So that's minus x over y. And this, of course, is y over x, which is also equal to minus 1 over x over y, right? Put a minus down here, right? So my point is that this, I'm just checking. I'm trying to make sure I didn't make a mistake since I already made one typo. As you can see, that dy dx is the negative reciprocal of what we started with, right? So if we solve that, it should give us the orthogonal trajectories. And we can solve this one, right? This is easy. What we got? I feel like we did this one already. dy over y. Am I missing a number somewhere? dx over. Oh, that's the thing. It's like the 3 disappears, right? Like the differentiation. So I'm sorry. We keep solving this. How many times have I solved this differential equation this semester? Good grief. I feel like this is like the 4th time. And so that tells us that y equals to kx. Those are your solutions. Really? Dang. That's not right. You know, the reason I have a class with students in it is so they can correct my mistakes. And if you guys aren't going to correct my mistakes, what am I to do?
negative sign.
Mm-hmm. Where? Oh, you noticed minutes ago. That makes it worse. How about here, right? Differentiating. This is minus, which makes this a minus, which makes this a minus, which, so that it's x over y, which then makes, well, you can make this a minus here, which then gives me like a minus here and a minus here. We'll erase this comment as it was irrelevant. And so lo and behold, we have I'll keep the minus on this side, minus, right? And what do you do with a minus outside a natural log? You just ignore it, right? And go on with your life, right? No, don't do that. This is the natural log of 1 over the absolute value of x, yeah? Plus a constant. Now, when I exponentiate this, it gives me absolute value of y is equal to e to the c times 1 over the absolute value of x, right? Take exponential. Which then gives me what? The solution, y equals to some constant divided by x. So there you go. That's your orthogonal trajectories. Now I think technically k equals to 0 is not allowed there because e to the c is really plus or minus, like that k is actually plus or minus e to the c, right? So technically speaking, the calculation I just did doesn't allow for 0 as a constant. But if you go back to the differential equation we're solving right here, right? Is y equals 0 a solution? It certainly is, right? So k equals to 0 is allowed. And you can even see that over here, right? This is k equals to 0. What does k equals to 1 look like? That's the reciprocal function, right? So that thing looks something like this, right? And then down here, right? Here's k equals to 1. What's k equals to 2 look like? K equals to 2 is a little bit further out. So it's something like this, right? Here's your k equals to 2. So the positive k's are going to give you this family of, the reciprocal function graphs, which, by the way, are hyperbolas. The reciprocal function is the graph of a hyperbola. It's just rotated 45 degrees. It takes the x and y axes as its asymptotes. And then, of course, if we looked at negative k, we would get these guys, right? So like here would be, for example, what's wrong with my voice today? K equals minus 1 for the purple. And then I'm almost out of markers here. So here's k equals 2 in the green. So for that given hyperbola, which I made in red, we get this infinite family of curves, every one of which, if we did the graphing correctly, when it intersects the given red curve, it meets it perpendicularly. That makes an orthogonal trajectory, right? So orthogonal trajectory problems are kind of nice in that you can check your answer, right? So if you make some stupid boneheaded sign error and you don't have a class to check your work, like me this morning, sorry, you're here, but you didn't tell me. So it's on you guys. Let's see here, Sydney. Is there an Owen? This is just a quiz from last time. Just trying to get back to you guys. Hand that back. Thank you. All right, so there's that. The other thing I wanted to do with markers today was to show you how we can solve second order problems by what's called reduction of order. So look at an example there. Example 2, suppose you wanted to solve y prime prime, I don't know, minus y prime equals to, let us say, e to the t. I may regret this, but that's what I'm going to try. How would you solve such a problem? You're like, I thought you said we're just solving first order problems on test one. Well, that's almost entirely true except for this class of problems. The only kind of second order problems I might ask you to solve on test one would be ones that we can solve by reduction of order. All right? Or to be more accurate, the only way I would insist on you solving a second order problem on test one is by reduction of order. We will learn an easier way to solve this later. So. But you've not had the course already, probably. I mean, I don't know who's had the course already, is what I'm trying to say. So that's not meant to be some sort of, you know, I'm not attempting to pour salt in the wound or anything like that. So what we do is we say y prime equals to v, right? And here the y prime is what? It's dy dt, right? If y prime is equal to v, what is y prime prime? It is v prime, right? Which, to be clear, I'm saying dv dt is y prime, right? So you see, I can take this given differential equation and I can do reduction of order by introducing a new variable, which you could think of as velocity. And I get dv dt minus v equals to e to the t. How do we solve this? What's that? Can we solve that? We can solve that, right? Imagine yourself after you're done studying for test one. You can solve this with confidence. Let's see here. You do not have to wait until the day before test one to do that. Like you could find that knowledge now. Like it's allowed. I always tell engineers, I realize that, you know, what's the word? Procrastination is held up as a virtue in engineering. I understand that. To study for a test in advance and do well, that's okay. To put it off till the day before and to manage to achieve to study to like an A minus with just 3 hours of work the day before, now you're a man among men. You have gained yourself reputation. Maybe my friend Crazy Paul was an engineer. I don't know. He was very proud of the fact that he learned Laplace transforms the day before the test in my differential equations class, and he managed to get a 70% with like 1 day studying. That was pretty epic. But I don't know. I love Paul. He managed to keep forgetting integrals and derivatives of sine and cosine like over and over and over again. I can't tell you how many times I told him, no, the integral of sine is negative cosine, yes. So this, sorry. I guess if I wanted that error, that's perfect. All right, see here. So the integrating factor is the exponential of the integral of minus dt, yeah? Because the function, the p, mind your p's and q's, right? Which is something no one says anymore because we're not like 120. But I'm pretty sure that expression died with a long gone generation. But this is e to the minus t, yeah? So that's my integrating factor. And as such, I multiply by that, I get e to the t, dv dt, minus v e to the minus t. Make sure I keep my minus. I've got a problem with that today. Oh man, this worked out nice. Oh, sweet. Look at that. It's beautiful. So do your reverse product rule. What do you got? You got yourself ddt of e to the minus t times v, right? Is equal to, what is e to the minus t times e to the t? Well, that's
1.
Yeah, that's 1, right? Now integrate this thing. What does it get? It gets you e to the minus t times v is equal to t plus a constant. I'll call it constant 1. Are we done? We're done with this part of it, kinda. So we can solve for v. And that gives us v, which is, by the way, dy dt, right? Equals to what? Equals to t e to the t. I knew there was going to be a cost to this example, plus c1 e to the t. The cost is calculus 2. How do we solve this differential equation? The same way you've been solving differential equations since calculus 1. Every time you find an antiderivative, you're solving a differential equation, right? Because you're asking yourself the question, which function can I differentiate and get back the integrand? That's solving a differential equation. So you might, in some sense, say that this whole course is about integration, right? Because we're trying to undo a differential equation. That's integration. That's mostly true for test 1, but it starts to be less and less plausible as we go on. At least it doesn't feel like integration. That starts to be really, really true in here on Friday. Okay? But anyway, so we can integrate both sides because the derivative is isolated, right? And when you integrate both sides, we get y is equal to the integral of t e to the t plus c1 e to the t dt. Right? And of course, you could leave your answer like this for partial credit, but I will take some points off because you do know how to integrate this. Or, well, you're supposed to know how to integrate this. I think you guys know how to integrate this. I'm going to be optimistic. You guys know how to integrate this. You do what? By parts, right? So I'll do the easy part, which is c1 e to the t. There you go. That's the integral of the first piece. And then I've got what? Plus the integral of t e to the t dt. I'll isolate the problem. So we're going to do integration by parts. That's my dv. That's my u. So u equals to t du is dt. dv is e to the t dt, which makes v equal e to the t. There's my integration by parts. And so, of course, we get c1 e to the t plus uv minus integral of v du. I'm writing it out because we might be rusty. Ha! Double bank shot. That feels right. Yes, sir. Uh-oh, what'd I do?
Fourth line?
Uh-huh.
Going from e to negative t dt over dt.
This to here?
Yeah.
Oh, that's the product rule. So differentiate this.
Because I see on the left side the blue line, right? You turn that into left side. Negative e to the t dv dt. You turn that into negative e to the t v.
Yeah.
And then you have the the d dt left over.
Oh, no, this is the differentiation. This is an operation. So when we differentiate a product, right? We do the derivative of the first times the second, plus the first times derivative of this, plus the second times derivative of the first, right? Product rule. And so the one derivative gives us minus e to the minus t, which is this term.
Right.
And the other term gives us a dv dt times e to the minus t, which is that term. So this right here is the so-called reverse product rule. And we should think through that every time we do integrating factor method, because if it doesn't work, you need to go back and fix your integrating factor, right? So it's good that you're thinking through it. Now here we have c1 e to the t plus t e to the t minus the integral of, well, e to the t dt. So what do we get? We get plus t e to the t, right?
Yeah, minus e to the t.
Minus e to the t, and then
Plus c2.
plus c2. And there you go. That, my friends, is the solution to this second order differential equation. Right? So can we solve any second order differential equation with this kind of chicanery? The answer is sorta, sometimes. Let me show you one in the notes. Okay, so one so here, while I'm getting the notes out, it's going to take me a minute for this to ramp up. In the meantime, see if you guys can solve it. Try to solve this one. See if you can do y prime prime plus y equals to 0. See if you can solve this one. So I'll get you started. That would be dv dt plus y is equal to 0. You should reach an immediate roadblock, right? What's the problem? You see the problem? Your differential equation doesn't just involve v and t, right? Like the example I just covered, well, no, it's still up there. The example there, the other one, you notice that there was no just plain old y term sitting there. So the pattern was different, and that's what part of what made it possible for us to just do it so easily. See, if there's no derivative, if there's no derivative in y term, then we need kind of a different approach. So here's how I did it. So okay, I'm solving y prime prime plus y equal to 0. So what I do is I use the d squared y dt squared is v dv dy, which is a joyful thing to say. But I'm using that trick I showed you last class, right? I'm trading a time derivative for a spatial derivative, and that changes my acceleration to this new derivative of velocity with respect to position. And then I've got v dv dy plus y equal to 0. Well, that I can rewrite in this Pfaffian form, and that's an exact equation, so I can just read by integration of both pieces that the solution to this is 1/2 v squared plus 1/2 y squared equal to a constant squared, right? So great. That gives us that v squared is equal to plus or minus the square root of some big constant minus y squared. But we're not interested in v on its lonesome, right? We'd like to solve for v as a function of t, right? So how does that go? Oh, sorry. Not trying to get you. So how's that go? Well, I've got dv dt equals to this. So I divide by that. I get dy over the square root of c squared minus y squared equal to plus or minus dt, right? But how do you integrate 1 over the square root? Oopsie. No natural log. I wish that we could just take natural log of whatever's in the denominator as an integral, but this is not how it works. So like this integrates to inverse sine of y over c by, say, trig substitution, or a clever u substitution if you like. And so I end up with inverse sine of y over c is equal to plus or minus t plus phi. And then if I solve for y, I get y is equal to the big constant times sine of plus or minus t plus a phase angle. And in other words, you can just repackage the solution as y is equal to a times sine of t plus a phase. This is what we guessed earlier in this class. Remember, we came to this differential equation and I asked you guys, hey, what function can you differentiate twice and get back negative the function? And one of you was like cosine or sine or something, right? My point to you is now we don't have to guess. We could actually derive it by using the techniques that we've talked about. I could integrate and then integrate again and solve for sine. I don't recommend this is actually how you solve this differential equation, right? So the thing is, once we know the answer, we can use it, right? So, but this is a derivation, right? A proof, if you will. So that brings us to our next topic, which is proofs. Well, not really proofs. So, once upon a time, differential equations used to be like an upper level math class. And so there'd be some engineers, but it would be more of a math major, more of a math major thing. Of course, it's not that way anymore, right? So the proof aspect of this course has decreased more and more. And it was not a proof course as long as I've been teaching it, right? So I'm talking about ancient history, like early 1970s, when 5% of U.S., in like 1970, 5% of U.S. College graduates had a math degree. It's now like 0.5%. Because computer science ate a bunch of our students first. And then various other applied math majors have appeared, which have siphoned off potential math majors as time goes on. Anyway, so we've talked about this stuff before. This stuff I talked about day one. I want to get to the theorems here. Talk about it a little bit. So this is a so-called isocline plot. These little dashes, all right, the slope of those dashes illustrates the value of dy dx at the point. So like this is for x dx plus y dy equal to 0. So if I was to solve for that, what would that give me? Dy dx equal to what? I don't think did I write it anywhere. Looking at it from a different perspective here. So if I solve for dy dx, what do I get? Minus x over y, is that right? So I think we get minus x over y. What happens when y is equal to 0 with minus x over y? Let's think through this. It's undefined, right? Which would mean we have a vertical line, right? Infinite slope, you could say. And that's what happens, right? Y equal to 0. Vertical, 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 right? If we put x equal to 0, we have 0 slope, also known as horizontal lines, as you can see. Chunk, 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 chunk. And then anywhere else where x and y are both positive, we have a negative slope. When x is positive and y is negative, we have a positive slope because minus and minus is a plus. Down here, we have two negatives, three minuses, negative slope. Up here, negative x, positive y. That makes this, again, positive slope. All right? So this is isoclines. It's just a little dash to indicate the slope of your solution by the tangent line that would be there. Okay? And as you can see, these are actual solutions to the differential equation, right? And this is created with a MATLAB thing. Actually, I think I created this with a Java applet, actually, truth be told, back before the Java apocalypse. Here's another one. Whoa, look at this. Dy dx equals to x plus y minus 6 squared. So here's the isocline plot. And I've just clicked. These dots, these are places where I clicked with my mouse, and then it traces the solution through that like that. All right. Here's another one. So as you can see, like the solution sets to differential equations, they have all kinds of different patterns, right? And this one I like. Check this out. So here's dy dx equals to x cubed plus x squared y minus x divided by xy squared plus x cubed plus y minus x, right? And that is a differential equation that it takes the unit circle as a sort of an exceptional solution, right? And then solutions that start inside the unit circle, they like spiral into the origin. And solutions that start outside of the unit circle spiral into the unit circle. But I know to me, this is probably the coolest first order differential equation that I have. I really like this one. I think you can look at page 38 to 40 of my handwritten notes. And if you look there, I have a solution of it by hand. I think it's just changing to polar coordinates, basically. But all right. So what's the theorem I mentioned? There are two theorems that we need to know about it here. All right, just two for this part of the course. I mean, for the first order part. And like you'll notice that we've never used these theorems, and we've solved dozens of problems, right? So these are not solutions. These are not theorems that we need to solve the problems, but they're reassuring. All right. So like the first one is the existence of solutions, and it says this: if f is continuous on a rectangle R, then at least one solution exists to dy dx equals to f of x comma y for each point in R. Moreover, these solutions exist on all of R in the sense that they can each reach the edge of R. So like if you've got a rectangle and you've got a function which is continuous on the rectangle, if I find a solution to dy dx equal to that function, it has to exist. There has to be at least one solution through each point in the rectangle, and that solution has to continue on to the edge of the rectangle. That's how it works. This is the existence theorem. And then another thing is we have a uniqueness of solutions sometimes, not always, is if we have, if we're studying dy dx equal to f of x, y, if we have that the partial derivative with respect to y of f is not equal to 0 at a point, then there exists a unique solution through that point. On the other hand, if your partial derivative was 0, all bets are off. You might have infinitely many solutions to your differential equation which go through that single point. So we wouldn't have a unique solution. We might have a plethora of them. So those are the two big theorems for first order differential equations, just that, right? And I'm teaching, co-teaching a class with Dr. Schmidt this semester, and we've called it advanced analysis, which just means it's a course past real analysis at the moment. And I'm teaching half the course, and in that half of the course, I'll probably prove one or both of those theorems. Probably just the existence one, but actually I don't remember. But I believe that the proof rests on something called, oh rats, what was the name of that thing? A Picard iteration. There's something called a Picard iteration. And if you study this Picard iteration, a fixed point of that iteration ends up giving you the existence of the solution here. And then it's an example of the so-called contraction mapping principle. And as such, it gives you like the existence of, it gives you a sequence of things that converges, and it also gives you a nice property for the limit of that convergent sequence, which ends up being the solution to the differential equation. But anyway, if this was a math major course, we'd spend a day proving it, you know, but it's not, so I'm sorry. And if I did, you guys would kick me out or something, which is fine. So how about this? dy dx equals to y squared. What is the partial derivative? So here, my big F of xy is y squared, yeah? What is partial f partial y in this instance? Well, it's just 2y. So if you believe the theorem, any place except for y equals to 0, we can do what? We can expect a unique solution to go through that point. But at y equals 0, all bets are off, yeah? So if you look at this differential equation, y equals to 0 is the solution at y equals to 0. And I think actually for this one, that actually is the only solution. So this one's kind of funny. It doesn't really illustrate the, like just because the partial derivative with respect to y is 0 doesn't force there to be infinitely many solutions. This example shows that. See, because this one, the solution set is, well, here, let me try to get something out. We're doing dy dx equals to y squared, right? All right, so I have to translate variables. This is d field. So we were just talking about dy dx equals to y squared. So I need to translate this into dx dt equals to t squared. That would be the analog in my software. Unfortunately, I don't know how to change the letters there. Yeah? So like, see up here, I have x prime, and it's really hard to see, but there's like a little prime. Do you guys see it? Right there. That's prime. So x, I guess I could do y prime. I guess I could put a different letter there. But, oh, wait a minute. I'm an idiot. Let's try this. I just noticed. Let's fix it. So I put, come on, cursor, do your job. Y t squared. Oops. And our independent variable is t. Wait a minute, but we did what before? We had what, y equals x squared? Wait, what do we have? dy dx equals to y squared. So I'm supposed to put a y here. I'll get it eventually, guys. X, right? All right, graph phase plane. All right, so here, so the way this works, I can't find the isocline plotter right now. I'm sorry, guys. I've looked, but these things. There is a routine you can download for MATLAB called pplane that will do some of this stuff. You can look it up. It's called dfield. I prefer like a Java, like a web app for this if I can find it. And I found one right now that works because I could put Java on my machine. I can make no guarantees for the school computers because, you know, I am not the boss of them. And I wouldn't want to be. So here we go. This is like, you can imagine making these little lines. The deal is they're all pointing to the right. So anyway, if I click here, here's some solutions. See that? But I don't think, so there's that y equals 0 right in the middle, right? I don't think this actually, I think there is a unique solution through every point, right? If I take any point on the x-axis, y equals 0 is the only solution that goes through that point, right? At any other point in the plane, if you've picked that point, there's just one of this family of curves which goes through this. So this differential equation actually has a unique solution through each point in the complex plane. All right? But let me get back to my notes here. If we go on, here's another one. We have dy dx equal to 2 square root of y. All right? Dy dx equals to 2 square root of y. So there my f is 2 times square root of y. What happens when I partial differentiate that? Well, I get 1 over 2 square root of y, right? Or I guess I'm sorry, I rewrote it. So I get 1 over root y. When is this not continuous? Like y equals to 0 is obviously problematic here, right? Not defined, certainly not continuous there. So on the other hand, if y is positive, it's continuous, great. And here's what happens. This is the graph. And so this is pretty cool. It puts red dots that are outside the domain of definition for the differential equation. So like dy dx equal to the square root of y, it's only defined for y non-negative. And as you can see, this time, the y equals 0 solution, it actually meets these other solutions. I think actually flow into it, I believe. Yeah. Because the actual solution is y is equal to x minus a squared. Y equals x minus a squared. It does hit the y equals 0 axis at x equals to a. So I don't know why we can't see. We should be able to see like parabolas if we could. Well, I must be thinking about it wrong. Let's think about this for a second here. We've got dy dx equals to 2 square root of y. It must be like, the solution must be like half parabolas. The half parabolas that start at x equals to a. Yeah. But again, this, we can do that over here. So like instead of that, I do square root of y. So the cool thing about this, guys, is if you learn how to use one of these visualizing tools, then you can see what your solution should look like, even if you can't actually, you can fairly clearly see what's going on here, right? These are half parabolas that start at the x-axis. And then every one of these intersects that exceptional solution of y equals to 0, which I can get by just clicking down here somewhere, hopefully, if I click right. Dang it. Well, I tried. Numerical methods is always a little dicey. Now, the other thing is that's pretty much all I have to say about existence and uniqueness, is that if we have a if we have the condition that the defining function, the f of x, y equal to dy dx, if the f is continuous, we have the existence of a solution near the point where it's continuous. If the partial derivative of that defining function is non-zero with respect to y, we have a unique solution. Those are the two theoretical tidbits I need to share with you for this material. That's pretty much it. Yep.
Does the size of the arrows have any significance?
I don't know. But this one here, you notice, like the previous one, all of the arrows were pointing to the right, because that was an equation of the form dy dx equals to f, like a dy dx equals to f of xy. So it actually, the truth is that other one actually uses this, and it just puts like dx dt equal to 1. So all of the arrows are pointing that way. This one, the length of the arrow is determined by the size of both dx dt and dy dt. For example, if I put dx dt equals to 0 and dy dt equals to 1, what should happen? Right? And now, to answer your question, all the same size because they're all the same length. If I, instead of making it 1, if I made y equals to, like, I don't know, y, what should happen? So there's 0, They're going to 0 at the y equals 0 axis, and then they're pointing up for positive y and getting longer as you go larger, and they're getting larger as you go negative. It's just the graph has shifted a little bit down. But we could do other things, like we could go back to day 1, like we solved x prime equals to minus y and y prime equals to x, right? We did that, I think. That was the one that gave us the circle equation. Here's the circles. Woohoo! So we can visualize solutions to differential equations using p-plane. Now this, I'm solving a system of differential equations. dx dt equals to a function, dy dt equals to a function. And so this is a so-called autonomous system. And we can directly visualize the direction field that corresponds, and then you're finding integral curves to the direction field, actually, is what we're doing when we solve the differential equation. But of course we can visualize it directly as well. So I do have one thing for you guys to do before you leave. And so I guess I'll, I don't know if I should cut off the video or not here. Probably I should.